In part 2 of Linear Regression Made Easy, we're going to be using SPSS to build a linear regression model against the entire employee dataset. So here we have a full dataset loaded in the IBM SPSS statistics. It's made up of 474 records, and as you can see, we've got these two fields that we've been looking at earlier on of people's current salary measured in dollars and their beginning salary. And if we wanted to estimate people's current salary based on the beginning salary, we could of course illustrate that using scatter plots. We could show the relationship between the two using correlations, and we'll just do that quickly. Let's look at salary against beginning salary. Click OK. The correlation value is shown here at 0.88 between beginning salary and current salary. It's very similar to what we had beforehand. But if we wanted to get a regression equation out that illustrated the straight line relationship, the linear relationship between these two fields, we would go to Analyze, Regression, Linear. We would choose current salary and put that in the dependent box. That's the thing we're trying to estimate. We'd use beginning salary as our independent field, and we'd click OK, and it would go and squirt out the results of that analysis to us. And right away we notice here that we get an R value, which we've seen earlier on. This is the same as the correlation value, 0.88, and the square of that is 0.775, so 77.5%, 77.5% of the variation in one field can be explained by the other. Generally speaking, within linear regression, people tend to quote what's called the adjusted R square value, which is always slightly lower. It's just a convention and takes account of the variability in the sample size, etc. The next thing we have is something called an ANOVA table. This is called an omnibus test. An ANOVA table here simply tells us effectively whether or not the relationship that we're looking at between these two fields is in fact entirely random, if the model is random or not. And if it's less than 0.05, we tend to reject that. It's usually less than 0.05. It's showing that the model is better than a wild guess. And then finally we get the coefficients table. And this is the table that we use to help us extract the formula for the straight line that represents the relationship between one field and the next. So let's have a little look at that. Taking a closer look at the coefficients table, this really represents the heart of the linear regression. And this is a simple linear regression because we're simply using one variable, beginning salary, to predict the values of current salary, our dependent variable. And the first thing we notice is that we have a number of values. The first one is the unstandardized B column that comes out. It's got two numbers. One is associated with a constant of 1928, and the other is a beginning salary value of 1.9. This relates directly to the equation for the straight line, the linear regression equation. In other words, for every $1 increase in beginning salary, it's worth $1.9 in current salary once we've added on the constant. So in other words, if we want to predict some of these current salary using this equation, we would multiply the beginning salary by 1.9 and we'd add on $1,928 as the constant onto the end. That would be our estimate. The next column is just a standard error column. That's a measure of variability or reliability of these statistics. That gets larger as the sample size gets smaller because it's not as reliable, and gets smaller conversely as the sample size gets larger, as the variability gets less. Standardized coefficients beta is really just the same as the correlation value here. It's no different from the correlation that we saw of 0.88. This only starts to get interesting when we have more than one term in the equation, more than one predictor. And then finally we have a significance test. Significance test is testing whether or not the constant and the beginning salary variable are actually helping us to predict the outcome. In other words, are they actually statistically significant? And they're both statistically significant because they're both less than 0.05. Now in fact, if we return to SPSS, we can rerun this procedure and ask it to save predicted unstandardized values for us. That just means raw predictions for us. Hit continue and OK. It reruns that procedure, but we'll notice here at the end we've actually got our predictions here in dollars. I'll just clean that up a little bit and remove decimal places, and I'll make the type dollar so you can get to see it. So this is people's predictions. This is the actual value, and of course we can actually graph this and say, well, show me the relationship between the prediction and the actual value. So here, if I go and say show me prediction against actual, click OK, we see quite a strong linear relationship here. This is the predicted value, this is the actual value, and that correlates to a R-square, as we've seen earlier on, of 0.774 if you're using the adjusted R-square, so 77% of the variation in one field can be explained by the other. Now, so far we've only been using one field to predict the outcome of the other field. What happens if we want to use more than one field? When if we do that, we're getting into multiple linear regression, and one could, for example, add in things like months since hire, previous experience, and education level. And here I'm using the enter method. The enter method means that it's going to force in these fields irrespective of whether or not they actually make a difference. I'll switch off the predicted values because we'll come back to that later on. And if I click OK at this point, we get another linear regression model that's built. This time the R value is much higher at 0.9. The adjusted R now has gone up to 0.8, so up to 80%. The ANOVA table is still significant, as we would expect. And now we have a different coefficients table with many more terms in it, all of which are being seen as significant at this point. Let's have a little look at that. Okay, so now we're looking at a multiple linear regression coefficients table. It's the same format as before, but this time we've got more terms in it. So we've got months since hire and previous experience. And when we look at the unstandardized B column again, this time the constant value is actually a minus number, so we're taking off $16,000. It means that the line now crosses the y-axis at minus 16,000. That's still significant, and it's not so much of a problem. It's a little bit unusual, but it just means that in order to estimate the outcome, we're actually taking the constant away from the final number. Beginning salaries now, we're multiplying that by 1.768 rather than 1.9. Months since hire is saying that for every extra month you've had since hire, your current salary is worth about $161 more. And amazingly, previous experience is saying for every extra month of previous experience you have, it's actually worth $17 less in your current salary. That's because some of the least well-paid people within the organization are actually much older, and that means that they've got more years of experience. So there's a negative correlation between age and their salary. Education level in years gets you, for every extra year of education, gets you an extra $669, so nearly $670 there. So now the equation's much more complex, and we can look at that in more detail in a moment. Once again, we have standard errors showing us the reliability of these values. The beta coefficients now are slightly different because the beta coefficients for beginning salary is still very strong. These are actually showing the correlation, or what's called the pure or partial correlation of each of these terms against the dependent field, which is current salary. It's a way for us to estimate which variables are most important in the equation. So beginning salary is definitely most important, followed by education level in years, followed by previous experience, followed by months since hire, going down in terms of the magnitude of those numbers. And every term is still significant at the 0.05 level, so they're worth retaining to estimate the outcome. So now our multiple linear regression equation is a little bit more complex than the previous equation because we have more terms in it. And if we wanted to show that, it would simply look like this. It would be current salary is equal to beginning salary times 1.768 plus months since hire times 161.5, which I'm just rounding, plus previous experience times minus 17 plus education level times 669.9, and then taking away $16,150. And that would be a slightly more accurate estimate of what people's current salary is. Now obviously you could pick up these terms and put them into an equation in SPSS and get it to estimate values for you on new data, and you could do the same in Excel. But it turns out in SPSS we can actually just save our regression model as a little file and apply it to new data. So if I do that, if I go to linear regression here, I'm going to get it to save a model for me. I'm going to call it salary regression. If I just tell it to put it in, let's say C temp or something like that, TC temp, I'll just put it there, say salary regression, click continue. It reruns the procedure as before, but it's saved out the equation in a little file. Now if I actually delete people's current salary here, if I delete it and pretend that we don't know what people's current salary is, we can then go to utilities, And using what's called the scoring wizard, if I point it to and browse for salary regression, where I put that C temp, there it is, click select and hit next, it maps it to the fields it's looking for. It's looking for beginning salary, job time, previous experience in education. Hit next, hit finish. It's going to create a field called predicted value. It's also going to create the standard error. We just want the predicted value. If we hit finish at that point, it's now created predicted value. So this is how we can apply a regression model from one file to another. We don't even need to know what the current salary is. We can simply, as long as we've got the input or the independent fields, we can produce these predictions. And that's linear regression.